Warm greetings and very good morning, dear students and friends. Today we are going to take about the video lecture on the bending stress, the case of a cantilever beam with the rectangular cross section, which is of width B and depth D. And all of you know that the pure bending equation is M by I is equal to sigma by Y is equal to E by R. We know the explanation of M is the maximum bending moment or the moment of resistance in kilonewton meter, and I is the moment of inertia about the neutral axis in terms of meter to the power 4, and sigma is the bending stress at any fiber from the neutral axis, that is given in kilonewton per square meter or newton per square millimeter. And y is the fiber distance from the neutral axis. So the fiber distance from the neutral axis is at a distance y from the centroid of the neutral axis section. So the maximum fiber distance is from the neutral axis y max is equal to half of the depth, that is d by 2. And capital E is the Young's modulus of the material of the beam, and R is the radius of curvature, and Y already we have defined as the fiber distance from the neutral axis. For example, I am taking a cantilever beam which is fixed at the one end and free at the other end, and it is subjected to an UDL throughout the entire beam. So W per meter run is the intensity of UDL. And what will be the maximum bending moment? The maximum bending moment occurs at the fixed end, and its value is the intensity of UDL W into L square by 2, which occurs at the fixed end, which will be of hogging moment, that is negative moment. So minus WL square by 2 is the maximum bending moment. So if you substitute the values of m, I, sigma and y, you can get the unknown factor, that is the bending stress in the beam. It is sigma is equal to m by I into y, where m is the moment of resistance or maximum bending moment. So here the maximum bending moment is WL square by 2, and I is the moment of inertia of the neutral axis, that is B into d cube by 12, and y is when it is maximum at the outer fiber, the top and bottommost fiber of the rectangular beam, which is of depth by 2, so d by 2. If you substitute the values of m, I and y max, you will get the corresponding value of the bending stress in the case of beam. So sigma is equal to the bending stress at the top and bottom fiber of the rectangular beam is equal to m by I into y max. So m is W L square by 2, I is B d cube by 12, and y max is d by 2. So if you are simplifying these values, you will get W L square into 3 divided by BD square. So 3WL square divided by BD square. So you will get the corresponding the maximum bending stress at the top and bottom fiber. For example, if you take this as a rectangular beam, so this is a rectangular beam of cross section. If you take it, which is of width and depth, width is a B and depth is D. So you will get the corresponding value of 3WL square divided by B into D square, where B is the breadth of the beam and D is the depth of the beam. So this is about the bending stress calculation for a rectangular beam. So it may be of a hollow rectangular section or solid circular section. In the case of a hollow circular section, you have to take the outer diameter is capital D, inner diameter is small d, means pi capital D power 4 minus small d power 4 divided by 64. So that is equal to pi by 32 into capital D power 4 minus small d power 4. So in that way you can get the value of the corresponding the moment of inertia about the neutral axis. So if it is a rectangular beam with a hollow section which is of outer width capital B, inner width small b, outer depth capital D and inner depth small d, you will get what will happen, capital B d cube by 12 minus small b d cube by 12. So you can take 1 by 12 outside, b capital B d cube minus small b d cube, and the corresponding value of y max here is the capital D by 2. You should not take small d by 2. So this is how the cross section is varying. You can find the corresponding bending stress, whether it is a solid rectangular, hollow rectangular, a solid circular section of the beam or the hollow circular section of the beam. If it is a solid circular section of the beam means which is of diameter small d, means pi d power 4 by 64. So that is the corresponding value of moment of inertia about the neutral axis. So if the maximum fiber from the neutral axis the half of the diameter d by 2, so either top fiber or bottom fiber, you will get the bending stress. So if you are drawing them bending stress distribution, so if it is a rectangular beam which is of depth d, means this is the center, outer and inner fiber. So at the outer fiber you will get maximum. If it is a cantilever bending, that is a tensile stress at the top, this is minus, and it will have a compressive stress at the bottom most fiber. So at the top most fiber will get maximum bending stress of tensile in nature. At the bottom of the section you will get the maximum compressive stress, because at the center or at the neutral axis point it will be 0. So the bending stress at this neutral axis or half of the depth from the top or from bottom, it is 0. So that is the thing we have seen in the case of taking a smaller example of a cantilever beam which are UDL throughout the beam, and section is the rectangular section which is a width b and a depth d. Thank you very much for patient listening. God bless. வாழ்க வையகம், வாழ்க வளமுடன்.